So today it's not even funny.
Let's take a look at the bell work here. So looking at this function, we are told f of x equal to negative 2x squared minus 3x plus 9. First and foremost, we are looking for the vertex form of our function. This is our form f of x equal to a times x minus h squared plus k. What information are we missing here? What do we need to find? H and K, fantastic. What should we start with? H is going to be what we're going to want to start with first. How do I find my value of H from all my useless information? Okay, fantastic. This is negative B over 2A, where in this case, what is our value of B? Negative 3. So this is negative 3, all divided by, and then 2 times, and what is our value of A? Negative 2. Fantastic. Negative 3 divided by negative 4 is positive 3 over 4, but we want the negative version of that, and so our value of H here, negative 3 over 4. Okay, these numbers are going to get a little bit nasty. Apologies for that. That is the consequence of my writing the problems from scratch without checking them to make sure that the numbers will be nice and clean. But that is okay. For finding K, couple of different ways to do it, but what's probably the easiest one? Just plugging the value of H into our function. So saying, well, I want to know what is f of H. I know what H is now. This is saying what is f of negative 3 over 4. Yeah, we can work that out. We'll end up with negative 2 times negative 3/4 squared minus 3 times negative 3/4 plus 9. I get that this is negative 18 over 16 plus 9 over 4 plus 9. And yeah, if you do the addition here, if you combine all the fractions, you'll get that that value of K should be 81 over 8. Really quickly, the way we would do that, 18 over 16 we could write as 9 over 8. So it's like negative 9 over 8. We want to match all of the denominators. So taking 9 over 4 and rewriting it as like 18 over 8, and taking 9 and rewriting it as 72 over 8, adding all of that together, you should get 81 over 8. Okay, so that's our value of H and K. Now it's just a matter of plugging it into our formula. F of X is equal to, what is our value of A here? Negative 2, the A that we see in our original function is still this A. X minus this negative 3/4 all squared plus this value of K, 81 over 8. All right, questions here with problem A, with part A. Yeah, Dylan.
I just need 81 over 8 back.
Say again.
I got 25 over 8 instead of negative 81.
When you squared your negative 3/4 and multiplied by negative 2, what'd you get?
But that should be,
Say again.
that was, I had that positive instead of negative.
All right. Taking a look at B, we are trying to find the zeros of this polynomial by factoring it. Polynomial, quadratic, same difference. So what's my factoring process? What do I do here? Two numbers that what? Multiply to make negative 18. Where does the negative 18 come from, Sumirnan? So you multiply A and C to get negative 18. Two numbers that multiply to make negative 18 that add to make negative 3. What are those two numbers? Negative 3 and 6? Negative 6 and positive 3. Yeah, right idea. Negative 2x squared minus 6x plus 3x plus 9. We do a little bit of grouping and a little bit of factoring. Factor again, drag out that x plus 3 term, and the zeros that I get, or the roots that I get, are x plus 3 and negative 2x plus 3. We are specifically looking for the zeros of this function. Those are the values of x that make each root equal to 0. So setting each of these equal to 0 and then solving, I get that x should be negative 3 and positive 3 over 2. Okay. All right. And lastly, with C, this was determining the end behavior of our function. If we are talking about end behavior, what is the only part of my polynomial that I actually care about? I've got 3 terms here, which is the only one that matters. The negative 2x squared is the only thing that I am going to look at for end behavior. All right. And then there were 2 different rules that we had to follow for end behavior. Where should we start? I like to start with what the coefficient tells us to do. So what does the coefficient tell us to do? So this fact that we are multiplying by negative 2 here, what does that mean? Yeah, fantastic. So as we move to the right, our function is going to be falling. In other words, I think the way Bryce said this is perfect. As x approaches infinity, our function is going to be approaching negative infinity. That's perfect. Visually, what is happening here? We are decreasing as our function is, as x gets larger and larger, our function is getting more and more and more negative. Okay? And then what does the squared tell us? So it's an even exponent, and even means that our other end is going to be doing the same thing or the different thing? The same thing. So on the other side of things, we are also going to be falling, and the way we might say that is as x approaches negative infinity, as we move to the left, our function is decreasing. We are getting smaller. So think of the as x approaches infinity thing as being the same as saying to the right. And think of the as x approaches negative infinity as being the same thing as to the left. And then what our function is doing, if it's going towards positive infinity, then we are getting bigger, we are increasing, we are rising. If we are going towards negative infinity, then we are falling in that given direction. And we could, of course, check this with Desmos, see what it has to say. And yeah, that is in fact exactly what we see. as x moves to the right, as we slide from left to right in that positive x direction, our function drops down really, really far. And as we move in the other direction, we see the exact same thing, that we drop down really, really far. All right, questions with the bell work here? Okay, we've got a few topics. One that I intended to talk about yesterday, but that I forgot about. So we'll cover it here. And that is the idea of the number of turning points in my polynomial. So let's say we have some kind of function here. Like this. Call this our polynomial here. And let's say I want to know what kind of degree that this polynomial is. How could I kind of go about answering that question? Well, the question is, it has a couple of different ways that we can kind of approach it. But one of the most reliable, or talking about like the potential degree for it, is to talk about the number of turning points that we see for this particular polynomial. Okay, so what do I mean by turning points? Turning points are going to be points which where we see our polynomial switch directions. So maybe we start out by decreasing and we switch over to increasing, or maybe we go from increasing to decreasing, what have you. Where do we find all of our turning points? Where do we see them? Say again? So we don't have like an equation here. So just like on the graph, where do we see our turning points? Where do we see points where we switch from increasing to decreasing? You're on the right track. The vertex is an example of this, but at the mins and the maxes, the relative mins, the relative maxes, absolutely at those, like effectively, if this was a quadratic, at basically the vertexes. So like here we would have a turning point, here we would have a turning point, here we would have a turning point, and here we would have a turning point. All right. Now, ultimately, our goal is to be able to take a polynomial and break it up into a product of all of its zeros. So we want to be able to take some polynomial and write it out, and this is kind of spoilers for the future, but write it out as a product of all of its zeros. The problem that we run into, though, is that sometimes there are zeros where there are not x-intercepts. In particular, we see this problem when we run into complex zeros. We saw this a little bit with quadratics. For instance, I could think of a quadratic that has no x-intercepts, that just sits above the x-axis, and it still has two zeros. We can still use the quadratic formula to find two complex values of x that would work as the zeros for this function. We can do that with all of our polynomials as well. And so while looking at the x-intercepts does an okay job at talking about kind of the degree of our polynomial, the maximum number of zeros that we are going to have, a better indicator for that is going to be looking at turning points. All right? Because every turning point that we see is going to account for at least two zeros. All right. For instance, we can kind of see it here. If I am going from if we're like starting to the right, working our way back, notice that we move in one direction, we cross the x-axis, we have to turn back around to then cross the x-axis again. So when I'm saying that that turning point is responsible for 2 of the zeros, I would say that this turning point is responsible for this 0 and this 0. Likewise, as we kind of continue down, we reach another turning point here. We turn back around, we cross the x-axis again. That's also going to run into a turning point that is responsible for this 0 and this 0. All right. And so we have this much kind of better metric, because as we continue going, we run into an issue, and that is that we don't have any more zeros, but we certainly have more turning points. And having turning points without an appropriate number of zeros clues you in on the fact that there are actually 2 complex zeros in the area. So here there are like 2 almost like imaginary, invisible x-intercepts that we miss by turning around too fast. And so when we are looking for what is the maximum kind of, I guess actually it's the minimum degree, in terms of the number of degrees that we have, a really great way is to look at turning points. If we want to think about it in terms of just like an equation, we might say that the maximum number of turning points that we can have is equal to the degree of our polynomial, that value of n, minus 1. So think like a quadratic, a second degree polynomial is going to turn around once. A cubic polynomial is going to turn around at least once, but you'd see up to twice. So like an x cubed graph, you would expect at least 2 kind of turnabouts. X to the 4th, you could see an x to the 4th graph that maybe only has 1 turning point, but you could also see one that has at most 3. All right. So the maximum number of turning points, we take the degree of our polynomial, it's that degree minus 1, and that gives us kind of a good clue as well, kind of working backwards as to what the degree of our polynomial actually probably is. Okay, so we'll look at a couple examples a little bit later. We'll do a bell work when we come back on Tuesday that has to do with that. Just something I wanted you to be kind of aware of. Turning points, we can define those as just like the points where we switch direction. And that's like totally fine. Or maybe the points where we switch from increasing to decreasing, or vice versa. All right. So any of those points where we switch directions, those are going to be the maxes and the mins. But now we have a new way to categorize them. Okay, now we talk about these turning points as being like a representation of like the maximum number of turning points that you could have being this, the minimum degree that you could see being this. It is possible for turning points to kind of not cover the whole picture, particularly if what is happening at the 0 is perhaps a little bit different than just one kind of route to 1, 0. In particular, we will see that the turning points are not a super great way to talk about the degree when we see repeated zeros of our function, or repeated roots of our function. So I want to consider the function, we'll say f of x equal to x plus 2 squared times x minus 1 cubed. I'd like to note that this is a 5th degree polynomial. If you multiply everything out, you'll end up with an x to the 5th out in front. Talk about the end behavior and all that. But what I want to focus on right now is I want to focus not on the end behavior, which we could certainly talk about, but we've already done that. I want to focus on what's going on around the zeros. In particular, I'm curious as to whether this squared or whether this cubed, what those are going to do to the behavior around the zeros. We've really only looked at these kind of roots showing up once up until this point. So let's see, is that going to change anything, or is this just kind of like a moot point? Nothing's going to happen at all. Spoilers, we're going to see some kind of change in our function based on the number of times that these zeros show up. Okay, so talking about these zeros, what are our zeros here? When is our function actually equal to 0? -2 and 1, fantastic. And then how many times does the -2, 0 show up? Twice. And how many times does that 1, 0 show up? 3 times. All right. And so what is that going to do to our function? There are a couple of different ways that we can think about it. We could look at the algebra behind what this is actually doing to our function. We could also think about this in terms of the local behavior of our function versus kind of the global behavior of our function in general. I'm going to try this with a slightly different approach than how I have in my other classes. Wasn't super satisfied with how these clicked. But what I want to kind of claim, and to this end, if you're interested in the exploration, we can certainly look at it during the time where we have classwork, where you have an opportunity to work on your classwork. But I think I'm going to go with this for here. For these functions, as we approach a 0, what we see dictate behavior is the root that accounts for that 0. All right. So what I'm saying here is that around -2, the x plus 2 squared part of our function determines the most behavior, determines the behavior. Okay. Likewise, around +1, the x minus 1 part of our function determines the behavior. There are a lot of reasons for this. Again, we could explore it algebraically. What we would see is that as we get close to a 0, we start to see very large changes in those roots that represent that 0, and we see very, very inconsequential changes in every other part of the function. And so the change in our behavior, how our function is evolving, is basically solely dependent on those roots. But what's kind of really cool about this is that that means that local to the 0, our function acts like an x squared graph. Or local to our other 0, our function is going to act like an x cubed graph. So around these zeros, our function is pretending to be what we see here, these repeated roots kind of determining what that function is going to look like. If we didn't have repeated roots, if I tacked on, let's say like an x plus 4 here, where we have a new 0 here, well, around -4, this x plus 4 is going to determine that our function acts like a line. And this ends up being a fairly powerful tool that allows us to graph these functions without really knowing anything more than their factored form. All right. So for instance, looking at this function here, we are saying that, I guess first and foremost, I'm going to get rid of the -4 bit. All right. We are saying that around -2, we are going to be behaving like an x squared graph. Now, if I multiply everything out here, notice that I've got an x to the 5th as my leading coefficient. So I'm going to be increasing when I'm moving to the right. I'm going to be going negative when I go to the left. So we're going to start off negative. And as I hone in on -2, my function is going to behave like a quadratic. In other words, it's going to, as I will describe this, it's going to bounce off the x-axis like a quadratic. So we hit that 0 and we go the other way, bounce off. Similarly, around 1, our function is going to be behaving like a cubic function. So we're going to kind of come in right around 1 and locally pretend like we are a cubic. In other words, we are cutting through our x-axis. We start negative, we cut through to the other side, we end up being positive, but we do it like a cubic function. We slow down a little bit first and then continue going. If we were to have included that linear term, we would have seen that it would also cut through, because lines, when they're going through their zeros, they cut through to the other side, but it wouldn't slow down like it was a cubic. It would just continue going to the other side. And in fact, we can confirm this behavior. We said we want this to be a 3. And what we see is exactly what we just described. The middle section is maybe a little bit blurry there because we don't know exactly what's going on. But notice around the 0 of -2, we act like a quadratic. And around the 0 of 1, we act like a cubic. If I were to change this 3 to a 1, we would see that it acts like a line as we go through that 0. It cuts straight through the 0 without slowing down at all. It just cuts straight through. Ultimately, this behavior can kind of be categorized into 2 different groups. We have our even powers, which tell us that we're going to bounce off of the x-axis, kind of like a squared. For instance, if we were to switch this to say, a 4, we would see almost the exact same behavior. Switch it to a 6, we see again almost the exact same behavior. What's the only real difference here between like 2, 4, and 6? What's happening here? It's stretching. It's getting like wider. We could think of it as we approach the 0 more slowly. It's actually the opposite is what's going on, but like visually it looks like we're approaching that 0. We're like slowing down around that 0. Really what's happening is when you take a number that is less than 1 and raise it to a large power, it approaches that 0 a lot faster. It's going to zoom in on that 0 at smaller or at farther out values of x, and so you see it kind of collapse in on that 0. But ultimately, we get this bounced off effect for any even power that we can pick. It doesn't matter, we could make it 100, and we get this really funny kind of like boxed effect because of how quickly it's kind of zooming in on 0. But either way, we get this kind of like reflection of we are bouncing off of our graph. bouncing off of the x-axis. And we could do the exact same thing for 1. We could switch it to 3. And we'll reduce this. This one's kind of muddying things. Keep that at 2. We could switch it to 3. We could switch it to 5. We could switch it to 7. And we get very much the same kind of result, which is that we are, again, kind of cutting through our x-axis, slowing down a little bit for larger values of the exponent. But this kind of idea of the odd exponent means we cut through the x-axis. Yeah, zoom in. Yeah, and the only other thing to kind of note is larger powers mean that you're going to be a little bit more wide. I think it would be unrealistic for me to say I want you to be able to tell that this is a to the 6th 0 rather than like a to the 4th 0. So you're not going to have to distinguish it at that level. But what I do think is realistic is being able to distinguish between when it is a linear 0 versus a cubic 0. I think that that is certainly something that we should be able to do. So we kind of have like 3 different behaviors. We have cuts through quickly, like a line. We have bounces off, like a quadratic. And we have cuts through slowly, like a cubic. And actually that follows those powers as well. And certainly we could do it with higher powers, but again, distinguishing between like a to the 8th and a to the 12th is so meaningless that we aren't going to do that. Okay. All this talk of like repeated zeros get at the multiplicity of a particular 0. So the multiplicity of a 0 is just the number of times we see that 0. In fact, it's a particular 0. And that multiplicity, particular 0. And that multiplicity and that power are the exact same thing. And this is really just as simple as you look at the power and you make a comment on whether it's going to bounce off or cut through. So for instance, looking at example 3 here, we are being asked to figure out the factors. I've factored a lot of these for you already. We're going to try and find the multiplicity of all of the zeros, and we're going to try to describe the behavior of our graph based on that multiplicity. So looking at example A here, we have 3 distinct zeros. What are our 3 distinct zeros here? Fantastic. -3, 4, and -1/2. What is the multiplicity of our -3, 0? 2, which means we bounce off. And I am fine if you want to use that vernacular. That's totally fine. What is our multiplicity of 4? How many times does that show up? Just once, which means that we are going to go straight through. So we'll say we cut through. And since we're going straight through, we maybe say we cut through quickly, right? We don't slow down like we're a cubic. We cut through like we are a line. All right. And then for -1/2, 2, which means we bounce off. Which again can give us an idea of what this function looks like. If we're thinking about, in this case, I'll say this is, technically I should have done it like this. If this is -3, -1/2, and 4, We are an x to the fifth. If you multiply everything out, you're going to end up with some positive coefficient times x to the fifth, starting negative, working our way. We reach our multiplicity of 2, we bounce off, we turn around, hit another multiplicity of 2, bounce off, turn around, and then hit that multiplicity of 1 where we cut straight through like a line. How certain are we of this middle stuff? No idea at all. No clue. Couldn't say. Probably pretty far off. But as far as the gist of the behavior of our function, it's going to look something like this. We can see exactly how close. I have this one actually already written. And it ends up being, again, a little bit far off. The dips and the bounces are a little bit more extreme than what we saw, but ultimately that general shape is exactly what we predicted. All right. Take a look at one more here. Looking at C, this one not factored for you. Oh no, I'm so mean. So we're going to need to work on that ourselves. We're going to need to factor ourselves. Factoring a fourth degree polynomial, a little bit tricky. What can we do at the start to make that a lot easier? Factor out we can factor out an x, but I think to make it even easier, we could factor out an x squared. I like that idea a lot. So bringing an x squared out to the front here, I am left with a 4x squared minus 12x plus 9. So multiplying the 4 and the 9, what are two numbers that multiply to make 36 that add to make negative 12? Positive or negative? Negative 6 and negative 6. From there, you could do your whole splitting thing. I'm going to cheat. I've done this problem. This is my third time today. So this is going to become x squared times 2x minus 3 also squared. But if you were to break apart and factor and all that, that's exactly what you would get, what you should get. Okay, so we have two zeros here, two distinct zeros. What are our two zeros? So I think 3 over 2 is 1. 0 is going to be the other. Yeah, so that's x squared times that 2x minus 3, right? So notice here, this x squared is what's contributing this x equals 0, 0. Okay? And what is the multiplicity? Well, the multiplicity of 3 over 2 is just going to be what? How many times does it show up? Twice. What is the multiplicity of x equals 0? Also 2, because this x minus 0 term, not really x minus 0, but this x shows up twice. Right? At that 0, our function acts a whole lot like x squared around that 0, which is going to look like a quadratic. It's going to look like a squared function. And so we would say it bounces off of both. You would end up with a function that, what was it? It was 3 over 2 and 2. You would end up with a function that looks like this. All right, questions about multiplicity? Multiplicity, which is just the powers of our zeros. And it's really just, if it's even, it bounces off. If it's odd, it cuts through. If it's 1, it cuts through quickly. If it's more than 1, it cuts through slowly. Yeah, why is it coming from above instead of below? So that is something that you can determine with the end behavior of your function. In particular, the leading term here is 4x to the 4th. And so we are going to end up increasing, and our opposite side is going to be doing the same. It's going to be going towards positive infinity. And so I know I start above, and I'm going to bounce off every time I hit the 0. So actually, we end up with a function that we can conclusively say is never going to be negative. Yeah. Yeah, you need the end behavior to determine, is it going to be this versus like this? But those two in tandem let you make that decision of which one is it going to be. Yeah. Yeah, very good question. Yeah, so it's the end behavior plus the zeros that let me draw this full picture. And that's actually the same thing for the one below. The reason why we know it's bouncing below is because according to our end behavior for that one, it'll be like something times a positive number times x to the 5th. And x to the 5th is ultimately going to be going positive towards positive and negative towards negative. And so you'll end up with this kind of behavior-ish. Good question. That's fair. I didn't comment on that as I was doing it. So that is very fair.
Wait, how is it 2 bounces and then it cut through? I thought it was x minus 3 is the bounce off, x4 is cut through, and then x is...
The negative 1/2 would be a bounce off as well. It's the order in which these come. So this is negative 3, this is negative 1/2, and this is positive 4. Yeah, so it's out of order from the equation, but we look at the order that it falls on the number line. Good question. Very good question.
Is there really a point of saying, like, originally I'm just going to move the first one, like x minus 3/3, like something we didn't do with saying multiply of 2?
A multiplicity of 2. So that's what tells us that it bounces off.
Oh.
Yeah, so that's like what we're using to like indicate it. No, not really. You're just kind of looking to, yeah, you're just kind of looking to that to say, around this 0, I would bounce off. Yeah, yeah. All right, one more thing to look at today, and that is something that I'm going to make sound significantly more complicated than it actually is. So focus on this kind of first part of what I say, and then when we actually write out the definition, try not to get too bogged down by the symbols that we're going to write. Focus on like the meaning of what we're talking about, because I think the idea is one that is very tangible, but writing out what it actually says can be a little bit tricky. So let's say we have some kind of polynomial function. And actually for this, what's important is not that our function is a polynomial, but all polynomials are going to follow this kind of property. What is important is that our function is continuous. Now, continuous is one of those math words that has a whole lot of very specific meaning that we are not going to unpackage in this class because this is not a senior level math class in undergraduate. So we are not going to worry about what I mean when I say continuous specifically. Also not a calculus class, so yeah, about what in particular it means to be continuous. For our purposes, a function is continuous if we see it's like an unbroken kind of curve, right? So there aren't any skips, There aren't any gaps. There aren't any like asymptotes or anything like that. There aren't any values excluded from our domain. So our function is like well put together. It's smooth. It's continuous. And actually smooth also has its own math meaning that we're not going to worry about for this purposes, all just kind of nice and flowy and connected, right? Let us then say that I give you a point over here on our graph. We'll define this point f of a, and we'll say that this point is equal to, so when x is equal to this x value of a, we'll say that this is, I don't know, we'll say positive 6. And I'll give you another one down here. I'll give you another point here. We'll say that this point is called f of b, and we'll say f of b, the output is going to be negative 3. Okay. If my function is in fact continuous, an unbroken curve, then in order for me to get from a height of 6 down to a height of negative 3, what values will I have had to pass through? Everything between 6 and negative 3. I will have had to go through 5 at some point. I will have had to go through negative 2 at some point. I will have had to go through pi at some point. I'll have had to go through 1 at some point. Every single value between 6 and negative 3, there has to be some x value between a and b where I hit that point. So, for instance, there's a value of c, f of c, where I hit 1. Where again, the only important thing about c is that it lives somewhere between a and b. There's another value of c. We'll call this like c1. There's another value. Oh, no, not that far. Can't confirm that one. There's another value of c. We'll say down here. Nope. We'll say down here, where we'll call this f of c2, where I hit negative 1. Do I know exactly what those values of c are? Not necessarily. But I know that they exist. I know that they have to be out there. I know they have to be between a and b. Now, it's great that our function hits negative 1. It's great that our function at some point between on this interval hits 1. But we are going to care more specifically about when it hits 0. All right. So while it is true that to go from 6 to negative 3, we must pass through all of the values between 6 and negative 3, more important to us is that to go from 6 to negative 3, we must at some point pass through 0. Okay. So there is an x value between a and b, where when we plug it into our function, the output is 0. Or in other words, there's an x value where the height of our graph is 0, somewhere again wedged in the middle of those 2 points. Now we can look at this function and we can make the observation that, hey, hold on a minute, there are more than one x value where that is the case. There are in fact 3. There are 3 x values where we hit 0. But that's not the claim we're making. All we're saying is if we go starting at 6, ending at negative 3, all we know is that we pass through at least 1 0. Right? This is the intermediate value theorem. This is what the intermediate value theorem says. Again, I'm going to put this into nasty math terminology, but that's the crux of the idea is if our graph switches from positive to negative or from negative to positive, then at some point we had to pass through 0, assuming our graph is continuous. If our graph can like skip, then obviously we can just jump over 0. But in this case, we're assuming that our function is continuous. So for f of x, a continuous function. Actually, maybe a better way to write that would be like let f of x be a continuous function. So we'll say let f of x be continuous. which again, for our purposes, just means no holes, no skips, no jumps, no anything like that. Right. So let f of x be continuous. And in particular, we're going to say it's continuous on an interval. So we can have a function that's continuous everywhere, but we just care about continuous on the interval a to b. So between the x values of a and b. If f of a is greater than 0, and f of b is less than 0. In other words, if f of a is positive, and by the time we reach f of b, we have switched to negative, or vice versa, then there must exist some value c between a and b such that f of c is equal to 0. In other words, if we switch from positive to negative, there's a 0 somewhere in the middle. Okay, I promised math jargon. I then did not deliver on math jargon. I was trying to translate very literally what I want you to write down and what I want you to know in terms of how I would have written this to be condensed. There is some value of c on the interval of a to b such that f of c equals 0, which is that entire paragraph that I just wrote, but written into a single line of math text. Yeah, say again. Sure. If you really want to, what you can write down is if we start positive and end negative, we must pass through a 0. That is the gist of what this is. Or if we start negative and end positive, then we must pass through a 0. If our function is what? Continuous. If our function is continuous. This is only true if our function is continuous. Okay. Okay, this is an incredibly important, incredibly powerful piece of math. There's a reason why it has this script, and it's very, very well used. This gives us a lot of power in calculus to do a lot of various things. And the good news for us is that it's an incredibly deep, incredibly powerful, and quite straightforward to use. This is one of those nice ones where the actual computation that we'll be doing is a lot easier than the big kind of theorem that we're using for it. I do want to make one quick comment though, and that is about what happens if our intermediate value theorem test fails. So let's say that we are given an f of b over here. We'll say that this f of b is equal to positive 2. So we started at 6 and we ended at 2. Can we conclude that there is a 0 in between those values? Did we have to pass through a 0 to go from 6 to 2? No, we didn't have to. Could we have? Absolutely, we could have, right? And we can see it in this graph. I could have just gone straight from this value to this value without ever passing through 0. That's certainly possible. But also, looking at this graph, I passed through 0 how many times on my way there? I passed through 0 4 times before I actually reach f of b. So if we fail the IVT test, if we fail the intermediate value theorem test, can we conclude for certain that there are no zeros between a and b? No. It's possible that we dip below 0 and then come back up, and by the time we're checking again, it's just no good. We missed it. We missed the window. And that's okay. It's just if our test fails, we just don't know anything. We can't say one way or another whether there are zeros. We just have to kind of shrug our shoulders and say, hey, there could be, but we have no idea. We have no way of knowing. Whereas if it passes, what we get is very specifically that there is at least one zero. It's actually not even all that much useful information. We get that somewhere in between there lives a zero. Okay, let's take a look at this. Example 4, use the intermediate value theorem to figure out if there is a zero in between the start value and end value that we are given. So all we're doing, checking the endpoints, seeing do we switch from positive to negative or negative to positive. So we are for A saying, well, what is f of 1? What is f of 3? And do we see that change? Well, f of 1 here, that's going to be negative 1 to the power of 4 plus 7. 1 to the power of 4 is 1. The negative of that, negative 1 plus 7, I get positive 6. F of 3, this is negative 3 to the power of 4 plus 7. 3 to the power of 4 is 81. The negative of that is negative 81 plus 7. I get negative 74. Have I switched from positive to negative? Yes, I have. And so is there a zero somewhere in between 1 and 3? Yes. Could there be more? Sure. But there's at least one. So by IVT, there is at least one zero between 1 and 3. At least one. And that's it. You just plug in the start, plug in the end. If we go from positive to negative, then fantastic, there's a zero. Let's take a look at C as well, then I'm going to give you guys the rest of this time to work on your classwork. So looking at C here, I'm trying to figure out if we have a zero, if we can tell if we have a zero. This is h of 2, which is equal to 2 to the 5th is going to be 32 minus 2 times 2, 4. So 32 minus 4, I get 28. And then h of 5. 5 to the 5th, feel free to double check me on this, but I think it's 3125, 3,125. And then minus 10, that should be 3115. Do we see a switch from positive to negative? No, we go from positive to positive. Does that mean there isn't a zero between 2 and 5? No. What does it mean? It means we have no idea what's going on. No idea, but we can't say that there is. There might be, there might not be, who knows? Can't say. Questions from anything from 3.3? So multiplicities, IVT. We'll get a little bit of practice with turning points. I know that one's a little bit hard to kind of see until we do work with it. We'll do a little bit of that on Tuesday. All right, got about 15 minutes left. You guys have the rest of this class to work on. Yes. Say again? Yes. I have the Once. Sure. One second.